And hello YouTube, welcome to our turbulence modeling series. So we've gone through a lot of theory and today we want to just talk about an example or a couple of examples in the OpenFOAM. If you're not using OpenFOAM, yeah, it's I guess good just to take a look at some concepts, but this is catered mainly for OpenFOAM users. You just want to do a simple conceptually simple case that give us some practice to set up and see what boundary conditions to use. So as you can see, I'm running right now a heat transfer case with buoyant pimple foam, 4 processes on parallel, and this is actually running the K omega SST IDDES model. And just for comparison, we can have the RANS model equivalent, which is K omega SST, and of course we'll try to do some semblance of something called quasi direct numerical simulation, quasi DNS, and that's of course our benchmark for comparison, since we discussed that data is very hard to come by. Getting the right probes and the right velocity and temperature readings near the wall is very difficult. So without further ado, I'll just introduce you to the case that we are considering today. So it's a simple case, and here is some of papers that I've been using. This one is called quasi DNS capabilities for OpenFOAM of different mesh types. So OpenFOAM can do DNS, no problem. There are just some caveats to it, alright? And of course there's a interesting one called DNS, direct numerical simulation of combined force and natural convection in a vertical plate channel. So that's the kind of case we are investigating today. So we're going to try quasi direct numerical simulation and compare that to our RANS model, which is K omega SST, and K omega SST IDDES, which is the LES hybrid model that we're talking about. But the main thing is of course to see, can we do DNS on a very cheap-ish laptop? Because right now technology has advanced. The DNS done in the 1980s, 1990s, they are done on the Cray computers, which apparently they have slightly lower computing power in terms of flops as compared to today's i5. So in theory, you could perform experiments done by 1980s, 1990s supercomputers on your laptop today. I'm using an i5 8300H, 8th generation high performance processor, 8 gigabytes of RAM, which is pretty standard nowadays. Of course, if you really want to run something a little more decent, you're going to need to upgrade some of those specs to do DNS. But for LES and RANS, those are perfectly alright. And for very, very, very mild turbulence, for example, just when you're just about to cross the transition from laminar to turbulence, DNS at that level is still okay. So, alright. First, why do we call it quasi DNS? Okay, it's called quasi DNS because it's not the so-called real DNS. Real DNS is done when you try to take a Fourier transform of your Reynolds average Navier-Stokes, and you break, because you do that because turbulence is kind of a periodic motion. So Fourier transforms and frequency domain data, meaning to say I break up my turbulence into all the various frequencies. That's very useful because it works for Fourier transforms work very well for periodic motion, and turbulence is one of those periodic motions. And basically you break up the turbulence into high frequency turbulence. Alright, high frequency turbulence, which is the turbulence that oscillates very quickly, and the low frequency turbulence, which is the turbulence that oscillates not as fast. And then you try to reconstruct this turbulence using polynomials, which and one term of the polynomial should correspond to some certain frequency. and these are called Chebyshev polynomials. I'm not sure if I'm pronouncing it right, but the idea is to break up this turbulence into various frequencies and use a polynomial, very accurate polynomial, to get as much fidelity, as much accuracy as you possibly can. So that's the real way of doing DNS. Unfortunately, OpenFOAM doesn't do too well since it uses this thing called the finite volume method. It cannot do as well as, let's say, this Chebyshev polynomial, but we can still simulate the turbulence using ultra fine mesh version of finite volume method. It's called quasi DNS, and it's done by this guy called Coleman. And if you compare with the actual DNS, the errors are very, very small. It's about 2 to 5% or even less than that. So the maximum error is small as long as your mesh is fine enough. So if you use a DNS type mesh, you should get pretty decent results from a quasi DNS based on the literature that you see here. So without further ado, we'll try a practice case for this quasi DNS, and I've gone through some of the steps already, if not most of 80-ish%. I just want to present the thought process behind it. Alright, so suppose you have a mixed convection flow in a planar channel. So what kind of channel is this? A planar channel is where you have, let's do this, a black background, and you have a channel like this, right? So let's say you have a flow going downwards, and we have mixed convection. On the left, we have T equals to 100 degrees C. On the right, we have T equals to 40 degrees C. It's a pretty decent number. And what is the fluid here? We say that it's some heat transfer oil called diatherm. Okay, so this is something I used in my heat transfer tutorials before. We'll give it, we'll try to give it some Reynolds number of maybe 3,200. Can't make it too high, if not DNS will just break down, or your computer will break down. Not DNS, your computer will break down because there's just too much turbulence. And we use diatherm A oil. Channel spacing here is about 1.5 centimeters. Okay, so how do you actually, so this is like a 1D kind of a flow, 1D-ish flow, except there is turbulence in here. That turbulence is 3D. So how do you decide how big your domain should be? Well, in literature, we have approximately this spacing. If we have a channel length like so, and we call this channel length H, right? So over here we will have equivalently, over here, I mean in literature, we'll have about 3 times channel spacing, and this is okay, just for reference, the flow is like this. So this is what we call span-wise. This is called span-wise distance, and yeah, span-wise distance, and this is the stream-wise distance. Okay, over here the length will be 8h. Alright, so this is a forced flow that's going downwards. There's gravity going downwards. Alright, 9.81 meter per second square, and hopefully your Reynolds number will be 3,200, or at least it's enough to get turbulence. So that's the initial Reynolds number I thought of, but later you'll find out why I can't use that. It'll be very interesting. Anyway, so 8h for the height, 3h for the span. So this is stream-wise, this is span-wise, and that's the domain. What are the boundary conditions you use? You use periodic boundary conditions. Okay, you use periodic BCs, boundary conditions, for temperature, pressure, velocity, etc. So that actually indicates that, hey, I am having this infinite flow, infinitely long flow of some oil that's flowing downwards, and then there is this oil. We initially set it at 70 degrees C, but after a while we will see that hey, this temperature here, 100 degrees, and this 40 degrees will act as these temperature boundary conditions will actually take over, the dominant temperature. Well, but if you see the average between these two, this average between these two is just 70 degrees C. So you'll see natural convection that's supposed to go upwards here. Natural convection is supposed to go upwards here, and this force flow is going downwards. Here you will have opposing mixed convections. Opposing mixed convection, and here you have aiding mixed convection. So this is sort of the accumulation of everything we have talked about. Sort of a capstone, so to speak, of an experiment that you can just do on your computer, hopefully, if the computer can take it. So we have opposing and an aiding flow, and we want to simulate this with DNS as far as we can. And of course, we want to compare how our turbulence models actually holds up against this quasi-DNS simulation. Oopsie, not going on Chrome. Anyway, so we have, as I said, these channel spacings. Channel spacing is 1.5 cm. Span-wise is 4.5 cm, or 3 times channel spacing. Stream-wise, 12 cm, or 8 times channel spacing. So this is a flow. Our mission, should we choose to accept it? Yeah, you have to do it anyway, whatever. We were supposed to, we're trying to run the simulation from, we'll try to have it at 65 flow through times. What is 65 flow through times? So you get that this flow will have a certain velocity, right? And then you have a span of about, a streamwise distance of 8 times the h here, which is 1.5 cm. Okay, so if you have this certain velocity here, and then this certain the span here, there's a length, so you will have a characteristic time where the fluid over here will reach the fluid over here on average. So this time is called the flow through time. Okay, it is this average velocity of this fluid divided by this length here. So we call it the flow through time, or FTT. This is what is shown in literature. So of course, when you start with an initial condition, it will take some time to settle down, right? It will take some time to settle down. And what is found in literature is that, okay, 65, 70 flow through times is enough, usually. Okay, but that's a pretty long time. Okay, and so this we have to give it some time to stabilize, maybe 65 flow through times, or some number of flow through times. If you're starting from scratch, 65 I think is a good number. It's from literature, and that's from if you do some calculations here. I'll show you what some of them are later. So we also want to get statistics for our velocity and temperature, right? So because we want to see how the velocity changes over time, it'll be very interesting to take a look at what the velocity is. Okay, so I'll be sampling velocity at some time intervals. It may not be the Kolmogorov time scale or whatever. I'll just sample it at regular time scale just to sort of give you an example. Okay. Yeah, so that's one thing we kind of take a look at. Yeah, of course we can do that average also of them. We don't just want raw data. We want to actually see what the mean is, and of course what the mean deviation from this mean is, the so-called standard deviation. They call it the root mean square. Okay, so this is actually seeing how much the turbulence actually deviates from the turbulent components, the u prime and everything deviates from the mean. Okay, and we use time averaging here. Space averaging is a little more challenging, so I'll not touch that yet, or not touch that first. Okay, so the thing is also we want to get in the heat transfer case. We are always interested in the friction coefficient and the Nusselt number. So we want to get time average friction coefficient and Nusselt number after we start collecting data. So this is an interesting problem. It seems pretty challenging. To set everything up from scratch. But thankfully, we will not need to set it up from scratch, alright? In OpenFOAM. There are some reference cases we can use, but we'll talk about those later. Let's get our Kolmogorov scale first. Our Kolmogorov scale is just 1 over Reynolds number to the 0.75 3/4 power. We have 0.0235, this ratio. And of course, it's important to take a look at our Batchelor and Kolmogorov scales for natural convection as well. They are presented here. I won't go through them again. And here I approximate Nusselt number as 0.15 times Rayleigh number to the 1/3 power. And that's for the Rayleigh-Bernard cell. Alright, Rayleigh-Bernard cell, meaning to say the hot plates at the bottom, cold plates on top, and then you have some natural convection. So it's a rough estimate, but as you will see, it's not so important. But it's just a rough scaling estimate. You don't have to be that precise with it, but it's just to give you a rough idea of order of magnitude. And we shall see how we find that Kolmogorov scale for force flows is definitely much smaller than even the Batchelor scales or the Kolmogorov scale for the natural convection side. Okay, and okay, interestingly for oil, for diatherm oil, our Prandtl number is about 16 ish, 16, 14, 18, thereabout at these temperature ranges. So definitely the Kolmogorov scales will be bigger than the Batchelor scales. So what we really need to take note of is the Batchelor scales. So for Rayleigh number, we first need to find our Grashof number. Grashof number is as follows: G beta delta T L cubed over mu squared. So how it's a bit of a big number, but if you take a look at this, it's very similar to Reynolds number. You have a nu at the bottom or nu squared at the bottom, you have a length cube here, and you just have G beta delta T, which sort of corresponds to the driving force. Okay, so anyhow, we have diatherm having a kinematic viscosity at about 70 degrees C of about 1.44 times 10 to the minus 6 meters squared per second. Your beta is this number, whatever it is here, 0.000802. The length we use here is actually half the channel height. Now, for channel flows, we usually like to take half channel height to be the reference length scale. Though, of course, I do find that channel height is a bit more convenient, but that's what literature uses, so we'll just stick with that. And here we go. So length is this, and gravity is this. The delta T is about 60 Kelvin. Plug everything in, we'll have Grashof number about 9.95567 or 9.55 times 10 to the minus or 10 to the 4. So just interesting to note that the Richardson number is about 0.0092. Richardson number is like the ratio of the natural convection to the forced convection kind of driving force. And for channel flows, actually your transition region is about 2300 to 2350 is found in literature. And at that, if you take the same Grashof number, the Rayleigh number, the Richardson number is about 0.0172. So it's a flow very much dominated by forced convection. So for Rayleigh number, we need the Prandtl number, and the Prandtl number is 19 and 70 degrees C. Okay. So we just multiply the Grashof number times the Prandtl number to get a Rayleigh number, and of course we want to plug this in to find out a rough estimate of Nusselt number, which is about 18.3 based on that. So the Batchelor scales are as follows: 0.01, and the Kolmogorov scales are much bigger, 0.05, this ratio, and we find that hey, this thing is actually much bigger, about 10 times bigger than this Kolmogorov scale. So we kind of just stick with the forced convection Kolmogorov scale, and that is enough. Okay, yeah. So it looks like this is the smallest. And how many cells do we need if we sized everything to this Kolmogorov scale? So the number of cells we need is actually the length of the domain divided by the Kolmogorov length scale, and that is just inverting this thing over. So that's actually 426 cells. That's a lot of cells actually. So we also want to have grading as well, so that the smallest cell size is actually about 1/10 Kolmogorov scale, and this is very conservative, and the largest cell size should be about 3 times Kolmogorov scale max. So based on this, give you a rough number. Smallest cell size we can take to be 0.5 times the Kolmogorov scale, and the maximum cell size is 2 times the Kolmogorov scale. This is actually quite decent. We don't have to go through the ultra conservative. We do not have computing power for that. So we'll try to give ourselves as much leeway as possible without damaging what without violating the Kolmogorov scale too much. So this we find that based on our last videos, the Kolmogorov scale is about 2 times the dimensionless distance at this point, and the smallest delta y plus, we want it to be about half the Kolmogorov scale. All right, so meaning to say that in the y direction, we want a y plus of 0.8. So my initial estimate is, okay, we take our Kolmogorov scale, we divide it by 2 roughly, just close an eye, so we have a delta y plus of 0.9, and hopefully that is half the Kolmogorov scale near the wall, as the smaller cell distance is good enough for us. So a give and take, right? So actually in the wall parallel directions, the streamwise directions, that's delta x plus is about 9, which is about 3 to 4 times the Kolmogorov scale. And span-wise, the distance is about, dimensionless distance is 4.5. Give and take is about 2 times the Kolmogorov scale. Alright, so what we need to do is to split our domain in half. So we have this domain here that we only need to split in half. Okay, I'll stop now. I'll continue more in the next video. Thanks for watching.